Hi, good afternoon. So I'm going to talk about our ongoing effort with accelerating the CICE climate model code called CICE on the GPU. So CICE is not an acronym for anything. I talked with the main developer of CICE, and I asked her, so does CICE stand for something? She said, no. Whenever I told people I worked on CICE, they thought it was C, the letter C, ICE. So that's the name that she imparted on the code. So first, I'd like to acknowledge the following NVIDIA engineers who gave great assistance with this effort, especially Matt, who's right there. He helped me a lot, tremendously, on a lot of OpenACC issues and resolving those. So the outline of my talk, I'm going to go over the CICE model very briefly, and then go into the strategy that we have been trying to accelerate CICE on the GPU. Then I'll go over some results, and then conclude with our path forward about how we might need to modify the strategy in order to get even better performance. So the CICE model is a global model for forecasting sea ice, the extents mainly in the Arctic region, and it only covers actual ice in the ocean. So there's a separate model for land ice, such as the ice on Antarctica or on Greenland. The CICE code is coupled to other atmospheric ice, ocean, land, global climate to give a global climate model. And the link there does provide you a way to get to the CICE source code. And it is a Fortran 90 code on the order of about 60 to 70K lines of code. It supports the following physics: transport dynamics and thermal column physics. Some of the gotchas that we encountered while we were doing this gave us a fair bit of headaches. First, you have to delete the device memory before you delete the host memory. Passing non-contiguous array slices creates temporary arrays. So the PGI, we've been using the PGI compiler. It injects allocation calls if you pass non-contiguous array slices. So when in a subroutine, if you have a present clause because you're expecting this passed array to be on the GPU already, all of a sudden we were seeing these errors that they weren't on the device. And so it took us a little bit to finally realize, oh, well, they're creating temporary arrays that were never moved over to the device. And we use assume shape. And one of the gotcha there was some of the physical quantity arrays in CICE have base 0. And so you have to explicitly declare that when you declare your arguments in your subroutine. So of course, with any strategy to accelerate code, first thing is profile, try and identify your hotspots. We use gprof to do that. It generates this very nice pictorial view of your profile. And then we just simply drill down to try and identify the hotspots, and here this a bit of a drill down into the dynamics portion. So originally, we wanted to accelerate the thermodynamics package first. The reason was that it doesn't require halo updates. It's a vertical physics, so it's grid independent. And we thought, OK, we can move all that over on GPU, leave everything on GPU, and do all our computations and wrap it up. However, CICE is going through this major refactor as part of the impasse effort. And part of that refactor, they wanted to extract out a lot of the column physics into a separate library that could be used by the existing CICE package and the new impasse CICE model. So that meant if we were going to accelerate this at all, we really needed inlining or the routine directive of OpenACC in order to make these calls, because basically we wanted to accelerate the actual calls themselves. So we tried this at the OpenACC hackathon that was being sponsored by Oak Ridge. So this was back in October. We first tried it with the Cray compiler, and in order to do inlining with the Cray compiler at the time, it required you to construct this very large database. So that meant our compile time went from a few minutes to about an hour. And if you touch any code, it had to recompile, it had to regenerate that entire database all over again. So touching even one, making one tiny change meant another hour of compile. So that was just not feasible. So then we tried the PGI compiler using ACC routine, but that just isn't working completely just yet. So we then decided, well, let's bite the bullet and go see if we can accelerate the dynamics package. So some of the challenges with accelerating the dynamics portion, there are frequent halo updates that are done between the computations. And additionally, there are many, many physical quantities that would have to be moved back and forth between the host CPU and the GPU device memory. So we need to try and hide those latencies as much as we can. The way we try to minimize the data movement, well, instead of having all these separate physical quantities that have to be moved back and forth, what we wanted to do was, can we just use a single large memory block and then just use Fortran pointers to point into slices of them? So now if we need to move the physics back and forth, we only have to move one big memory chunk. And this did work, where you just have your physical quantities now declared as pointers pointing into these individual slices. Next, we wanted to see if we could use CUDA streams to try and hide some of the latencies with data movement. So if loops are data independent, then we launch them using separate streams along with the data updates back and forth from the host to the device. Additionally, when there are calls to subroutines contained within loops, and each call is loop independent, we do a similar thing where we pass the loop iterator as a stream value. And so within that subroutine, all the parallelization that we do use that stream value. So in essence, we're launching n kernels. When we looked at the profile of a typical CICE run, it's very dominated by MPI. That is, MPI is a big bottleneck for CICE, to the point where it can consume greater than 35% of your total runtime is dominated by MPI. So we wanted to look into using GPUDirect to see if that can help us get around the MPI bottleneck and find a solution for handling these halo updates. So we built CUDA-enabled OpenMPI 185 on Moonlight using the PGI 14.7 compiler. We were also doing runs on Oak Ridge's Titan machine. And Cray already has a CUDA-enabled version of MPitch. And furthermore, it also supports the MPS service. That is, so the MPS service provides a mechanism for multiple MPI processes on a single node to use to share a GPU resource. Without MPS, if you try and use the same GPU, those kernels essentially get interleaved, and there's a lot of context switching that goes on. And that actually is what happened when we start looking at the results later on for Moonlight. However, the XK7 doesn't truly support RDMA. So underneath the MPI library is pipelining everything through the CPU. But at the very least, if we put in the effort now to use GPUDirect, that prepares us then for Sierra and Summit coming up. So the way we did this is we took all these multiple Halo updates, and the current code, CICE code, when it calls a Halo update, each Halo update call is synchronous. That is, it will do iSends and iReceives within the Halo update, but then there's a wait all at the very end. So effectively, every Halo update call is synchronous. So one strategy we wanted to try out is get rid of that if we can. So we use Halo begin and a Halo end. It's here. We identify how many fields need to be updated for the Halos, and then we simply modified the Halo update calls to be asynchronous. So we just dispatch the MPI communication and then return immediately, and then everything gets finalized in the Halo end call. So the rationale for this structure is that this then gives us a way of initiating some Halo updates, and in between these Halo updates, perhaps we can do some more work on the CPU of doing some computations that's not dependent on those Halo updates just yet. Okay, so I'll go over some of the results. We used 2 test problems for this. One was a very small, just normally running on 16 MPI processes with grid size of 320 by 384, and then a slightly larger one that normally runs with 60 MPI ranks. So we run with, so CICE gives you an option of how you want to define your block. Typically, rectangular blocks on a sphere. That's a typical way of running a simulation on the sphere. But with CICE, at any given time, CICE only covers 4% of the Earth. So 96%, it's not really doing anything. So to kind of alleviate some of that load imbalance, you can define longitudinal block that runs all the way from North to South Pole, and so at least you have a chance where each block might have some work to do. We used Lano's Moonlight cluster, which is a GPU cluster where each node has 2 NVIDIA M2090s, and we also ran this on Oak Ridge's Titan machine, which has 1 K20X, and in both, we use the PGI 14.7 compiler. One problem with the, Titan machine is that right now, it's limited to CUDA 5.5. It's in the process of upgrading. They're in the process of upgrading to, I think, 6.0. But there are some hardware issues that they're trying to overcome right now to do that. And recently, NVIDIA was very kind enough to get me onto their PSG cluster. So I was running this on nodes that had 6 K40s per node, and running that across 10 nodes. And on that platform, I was using OpenMPI 1.8.5. Okay, so if we look at the P4 problem, which is normally a 60 rank problem, and looking at the baseline compared to the OpenACC and GPUDirect, whoops, wrong one. We are not doing too well, but I'll go into this in a little bit, explain what's going on here. If we play around with the rank distribution, that is, keep the ranks the same, and look at performance if we run over 4 nodes, 6 nodes, and 10 nodes. If you look at the comparisons to Titan, we get better results as we spread over more nodes. What's odd, and we haven't been able to really explain what's going on here, but on Moonlight, it actually goes back up in time. We're not going to put too much effort into trying to improve this on Moonlight because it's M2090s. They're old. And they don't support the MPS service. So we're going to focus more on getting improvements on Titan and also on PSG. So on PSG, part of the reason why we're not doing too well is that we didn't have the MPS service enabled. I did try that this morning to try and get it to work, but we were getting some runtime errors creating CUDA context. So hopefully we can get that resolved soon, so that way we can try it again. So without MPS, and you're running 15 ranks on a single node trying to access six cards, you're going to run into the context switching problem. And that's what's going on there and inhibiting performance on it. And if we look at scaling, going from 10 ranks up to 40 ranks, we're actually doing better, at least on Titan, where we're actually outperforming the baseline. And there, it does have MPS enabled, so that might explain why we're actually seeing better performance, at least on Titan for now. Okay, similarly on PSG, when we do the same scaling, we're actually doing worse. And even when we reduce it down to 5 ranks per node, so that means each rank does have a dedicated card, it's still performing quite a bit slower. So I was talking with Jerry Krause about this, and he thinks the reason is due to GPUDirect. That is, there are 6 cards, but they're spread over 2 sockets. So when you're trying to do RDMA over the InfiniBand card, and it has to access memory from all of those cards, it's akin to doing a NUMA, or having NUMA effects. That is, you're going across NUMA domains in order to get memory on a card that's on a different socket. And so you're incurring penalties from that. So one nice run that we'll have to try is if we limit this to only those devices, enable MPS, and then limit the devices to only those devices on the same socket as the InfiniBand card, and see if we get better performance that way in that mode. So one nice command that kind of helped illustrate all this is NVIDIA-SMI topo-m. And so this kind of gives you a layout of all the devices and the path that it would take to go from the InfiniBand card to these individual GPU cards. So if you look at GPU cards 4 and 5, it's going over a socket level link. So when we're running, so in that previous case where we were running with 5 ranks on a node, that meant in one of those instances, it's going to have to go over this much slower path to get the memory from that card. So conclusion, we want to try and see if we can improve the performance of GPUDirect. For example, in those cases, and that pitch is going to be releasing a topology-aware CUDA-enabled version. So we want to try that and see if that will help us with GPUDirect. Can we also restructure the code in order to get better communication computation overlap, such as what I was trying to described before, where we can start Halo updates and in between do as much independent computations as we can while the Halo updates are being performed. And also, can we find additional task parallelism so that way we can combine OpenACC with OpenMP. That is, if there are cases where we can't, where it's going to be too costly to try and execute on a GPU, well, let's do what we can on a GPU and at the same time identify smaller kernels that could then be accelerated with OpenMP. So that's kind of the strategy that we're going to go down as we move forward with this. And thank you for your time.